In the previous video, we learned the notion of value function learning, in which the values of states and actions were estimated, and then these values were used in order to determine which actions to take. In policy gradients, the probability of each action is directly learned in order to maximize the long-term reward. In the previous lecture, we discussed value-based methods like Q-learning that attempt to predict the value of an action with the use of a parameterized value function. The idea in these methods is that the predicted value of a function can be used to pick the best one. In general, these methods couple the prediction of the values with a generic policy like epsilon greedy, which combines exploration and exploitation in order to pick the best action. Policy gradient methods are, however, somewhat different because they model the probability of each action at each step with the goal of maximizing the overall reward. Therefore, the policy is itself parameterized. So, let us take a quick look at the policy network versus the Q network for the Atari game. Now note that I had used the Atari game for the case of the value network. So it's easy enough to use the same example for the case of policy networks. On the top, I have shown the convolutional neural network, which is the Q network for the case of the Atari game. This is a network which I had already introduced in an earlier lecture. In this case, you can see that the input is essentially the state of the game. And in the case of the Atari games, we had used the previous 4 snapshots of pixels as our input state, and it produces an output which is the Q value of each action. So let's say that in your Atari game, you have a joystick which has 4 possible actions corresponding to up, down, left, and right. So in this case, the neural network, in the case of the value networks or the Q networks, which we had discussed in the previous lecture, it tells you what is the long-term value of playing up, what is the long-term value of playing down, what is the long-term value of going left or right, and then you will couple it with a generic policy like epsilon greedy in order to pick the best of these actions. Now, in the case of policy networks, the approach is somewhat different. In the case of the policy network, the input is still the same. Again, we are using the previous 4 screens of pixels. So that's basically the state of the system, whatever feature representation you use for the state of the system. And the output directly gives you the probability of up, down, left, and right. So in a sense, it's directly outputting the probability of the action. So in a sense, you'll be using these probabilities for sampling. So that is how the approach is going to proceed. That in each step, your neural network is going to output the probabilities of all the actions. You're going to sample one of them based on these output probabilities. If that's going to change the state, and you're also going to get a reward. You're going to go back to the input with this new state, and then again it's going to output the probability of the next step. Now note, of course, that here you will have to somehow learn the parameters of the neural network, that the output probabilities, that the policy that you learn maximize the long-term rewards. And this is the main challenge in policy gradients. In the case of the value gradients, the nice thing is that because you're trying to model the long-term values and the network is also outputting the values for the actions, it's relatively easy to set up a loss function. In the case of policy networks, it's somewhat more difficult because now you have probabilities of outputs and you want to maximize a gain function. I'm calling it a gain function because you're maximizing it. So rather than a loss function, I'm calling it a gain function, which corresponds to the expected long-term reward. So this subtle difference between the way policy networks go about trying to learn and the way in which value networks go about to learn is reflected in some complexity in computing the gradients for policy networks. And we'll see this in later slides. So let's take an overview of the approach. So essentially what we want to do is that we have this policy network and we want to update it over time. And the way we want to learn its weights so that it maximizes the expected long-term reward. So what you want to do is that this neural network that you're learning, you want that the probability that it outputs are such that when you sample them over time, when you sample the actions using these probabilities, then the expected long-term rewards are as large as possible. That's your goal. Now, of course, you also want these, in order to do this learning, an important part of the training data is the samples of the long-term rewards. So every time you perform an action, so for example, here you have probability of up, probability of down, left, right. So every time you simulate an action, let's say you sample up and you take the action. So you need a way to be able to compute the long-term rewards for performing this action. Now, this is not very different from what actually happens in the case of Q networks. And you can use similar types of methods. One, of course, is Monte Carlo policy rollouts to estimate a simulated long-term reward for each action. So what you can do is that for this neural network, so for example, if you're playing an Atari game, then at each step of the game, you can sample a priority, move to the next step, then again sample the next action and so on. And then you can collect the rewards over all the states and you can compute the expected long-term reward using this simulation. So that's your standard Monte Carlo rollout. The other approach is that you can actually have a sister network. This sister network can model the long-term reward for each action. The sister network is essentially a Q network. And this idea is the essence of actor-critic method. So we'll first start off with the Monte Carlo policy rollouts and then we'll discuss how one can make it faster by using actor-critic methods. Now, another key point in this type of approach, of course, is in terms of setting up a loss function. In fact, as we'll see, it's a gain function that uses the simulated or modeled rewards. Now, you're simulating these rewards. So you have all these samples of rewards and you want to somehow use it to update the parameterized probability that the expected long-term reward is maximized. So the point here is that you have samples of rewards based on certain actions you picked. And based on these samples of actions and the rewards, you somehow want to update the weights of a neural network so as to maximize so that the neural network learns the policy that maximizes expected long-term rewards. So now let's start off with collecting this type of training data. As we discussed in the previous slide, the training data will correspond to the actions that the actions that you perform as well as the long-term rewards for each action that you perform. So let's say that we are going to use a chess example, and let's say that we have an artificial chess agent, a learning agent, and let's call her Alice. And this agent Alice, we have a pool of human opponents available to train our artificially intelligent agent Alice. And the reward given by the environment is that when the game is continued to termination, at the end of the game, Alice will get a reward in 1, 0 or -1, depending on whether she won, drew or lost the game. So we can perform a Monte Carlo simulation for agent Alice, and let's say the human opponents are there to participate in this Monte Carlo simulation. So every time a move is made, the human opponent makes a move, and then Alice goes to her policy network and she runs it through the policy network, gets probabilities of actions, picks one of those actions, and this entire process is carried through to termination. And at the end of termination, let's look at a particular game in which, let's say, Alice wins. So in this case, let's say that this game lasted for 50 moves. So there were 50 moves made by Alice and 50 moves made by the human opponents. So for each of the 50 board positions that Alice faced, you will generate one training point. And the features for this training point correspond to the state of the board. And then you will have a long-term reward associated with this training point. Now, since this game was a win, you will assume that in this case, the long-term reward is 1. Now, this of course assume that your reward discount factor, that gamma is 1, but you might have gamma less than 1. In that case, the reward for a move is gamma to the power r minus 1, where r is the number of moves to termination. So, for example, the final move that Alice makes to get a checkmate, that gets a reward of 1. because r is equal to 1. Then the move just before that, you have r is equal to 2. So she gets a credit of gamma. And then at the very opening, the very first move that she makes, she gets gamma to the power 49. That's your standard horizon-based discount in these types of reward functions. Now note that if you had performed the same simulation with, for example, an Atari game, you might get continuous rewards over time. So you might get a reward at each timestamp, in which case you would have to sum up the rewards, the sum of the discounted rewards that one gets over various timestamps. So this is essentially the training data that you collect. So you have these states. You also collect the sampled action as well as the probability of that action, the one that you sampled. Now the main issue is that how do you use this type of training data in order to in order to change the parameter of your neural network. So you somehow need to update the neural network from the samples of long-term rewards. So all you have is samples of actions and samples of long-term rewards, and you're trying to maximize the expected rewards. Trying to maximize expected rewards from samples of rewards is not obvious, because now you have to compute the gradient of an expected value. Now, look at the situation over here. Look at the nature of the training data. You have these board positions and the output action samples a long-term reward for each sampled action, but you don't have the ground truth probability. So one issue in policy gradients, which is very different from value networks. In value networks, you're trying to model values, and you can model and you can also simulate what the ground truth long-term value is using Monte Carlo simulation. So it's very easy to set up a loss function to set up the targets, because what you're outputting is very similar to your ground truth value. Here, your problem is that you're outputting probabilities, and what you're getting is that what is a long-term value of the action you selected. You don't have the ground truth probability. So an important question arises is, how do you maximize the expected long-term rewards from samples of the probabilistic output? Because here we have to compute the gradient of an expectation. Now, computing the gradient of an expectation is always challenging, because most of the time with neural network backprogramming, we are computing the expectation of the gradient, which is relatively easy because expectation of gradient, it is additive over the different samples. But computing the gradient of an expectation from samples suddenly becomes a lot more challenging. So let's look at how this is done. And this is the key trick that is used in policy gradients, which is called a log probability trick. And this was proposed in the original reinforced algorithm using this type of trick. So let's say that at a particular state, ST, where an agent has made a particular action. So for example, in an Atari game, there will be the state of the video game, and you might have picked up the action up, and you get a certain long-term reward. That's QPSTA, which you estimate using Monte Carlo simulation. So in our chess example, for example, our action would be the move in chess you made, the state would be the state of the board, and the reward would be depending on if Alice won, it would be gamma to the power r minus 1, as we saw in the previous slide. So that's your QPSTA. And what you want to do is that you want to maximize the expected value of QPSTA. So this is like your gain function. We are calling it a gain function because we want to maximize it rather than a loss function. So you need to perform stochastic gradient ascent because you're trying to maximize the gain function. Usually in backpropagation you perform stochastic gradient descent. So here, in order to perform the gradient of an expectation, and this is the key trick, you can show, this is called a log probability trick. This is equation 11. I will not give the derivation of this result. The derivation of this result is in the book. You can show that this gradient of the expected long-term reward is given by the expected value of this long-term value. You remember this QPSTA, you got it using Monte Carlo simulation. So you have this value multiplied by the gradient of log PA, where A is the action you selected. So for example, in our Atari game, let's say you selected up. So you will, just for the output up, you will backpropagate from that output. So your gain function will be log of probability of up. You will backpropagate from that gain function, and the weight will be the gain that you got from that action. So let's say when you move the joystick to up, when you selected up, so it gave you certain probability of up, and you selected that action and you did really well in that video game. So your QPSTA will be very high. So use that to weight this gradient, because it gives you some feedback that, hey, this action was good. And that is how you'll compute this gradient of the expected, and then you will use it to update the neural network weight parameters. Now note that this gradient of log probability, this is relatively easy to do, because this gradient of the log probability, essentially it's pretty much like the kind of gradient of log probability you compute in softmax classifiers. Remember that in softmax classifiers also you have these cross entropy losses which use the log probability. This is very similar, except that in this case it's a gain function, and you are also weighting with the reward QPSTA which you got using your Monte Carlo simulation. And then what you're going to do, you're going to update your weight vector after you're computing this gradient using backpropagation, by backpropagating the log probability in your neural network and then weighting it with the Monte Carlo simulated long-term reward that you got. You're going to update, and here alpha is the learning rate. This is equation 12 is your update. Now, what I presented was the simplest form of the updates. Now, usually this weighting, you see that here in equation 12, I use the weighting as QPSTA. Very often one does not directly use the long-term reward. One actually adjusts it with a baseline. You can think of adjusting with a baseline almost like mean centering the reward. So what you do is that you take some constant value B, which is some long-term measure of average reward that you are expected to get. And if you look at the original paper, the reinforced paper that Williams wrote, there they are using a constant baseline. And you subtract that constant baseline from this long-term reward. So there's some constant baseline. So at every point in the game, there's some average reward you expect to get from the future, and you subtract that from the reward for performing that particular action. Let's say you perform the action up. And that, if it's positive, it tells you that performing this action is good. If it's negative, then it tells you that performing this action is bad. Now, it's relatively easy to show that adjusting with a constant baseline, it does not affect the bias of your result, but it does reduce the variance of your result. So it helps in avoiding overfitting. And this type of baseline adjustment with a constant is referred to as a state-independent baseline adjustment. Now, there is another form of the baseline adjustment which is more principled, where one can choose the baseline to be specific to that input state. So let me go back to the neural network. Here. So what you can do, let's say that at a particular state, there were certain probabilities for various actions. And let's say you sampled up. So you got a probability of some 0.2 for up, and you happen to sample it. And then what you do in this case is that the baseline that you use is the value of the state before knowing which action you would have picked. So what you do, your long-term reward will be the after sampling up whatever reward you get. But you can also have an expected value of the state before knowing which action you would have picked, and you take the difference of the two. Now, this difference is essentially the same thing. You can show that it's the same thing as temporal difference, which is what we use in temporal difference learning. So if you choose B to be the value of the state, then essentially you're subtracting the value of the state ST, that is without knowing the action that you picked, from QSTA, which is a temporal difference, which is a difference of one step. So in this case, the advantage is the same thing as your temporal difference. This makes a lot of sense because temporal differences, they carry a lot of intuitive information about the unexpected effect of that particular action. So if a temporal difference is positive, it tells you something unexpected about the long-term rewards with respect to what you expected before knowing that action. That's a very useful kind of quantity to use in order to weight your updates. So let's look at it in a little bit more detail as to why a state-specific baseline adjustment makes a lot of sense. So imagine that you have a self-play chess game in which both sides make mistakes. So let's say that you have two agents, Alice and Bob, And both Alice and Bob makes mistakes, but Alice makes minor mistakes and Bob makes serious mistakes. So in the end, Alice wins. Now you use and let's say that you use this Monte Carlo simulation to update the neural network, and you can use the training data for both agents, and for each agent you update from the perspective of the agent. So from the perspective of an Alice, the long term reward will be a win, and from the perspective of Bob, the long term reward will be a loss. However, the main problem here is that when you look at all of Alice's example, every position that Alice played, even the mistakes she made, even the minor mistakes she made, she might have ended up in some bad board position, but she still gets a credit for a win. Now, that is why, because of this, you need more data to understand which mistakes are more serious and which mistakes are less serious. And that is why when you don't make the adjustment, the variance increases, the variance of the assay. You need more data to disambiguate these different positions. On the other hand, if you use temporal difference, what's going to happen is that every time Alice makes a mistake, the temporal difference error is going to tell you something more immediate. It's going to tell you something more immediate that, hey, Alice has made some mistake. And that will give you a more refined idea of the effect of that move. And that is why it's sometimes advantageous to use a state-specific basis. It's helpful to use the temporal difference as the advantage rather than just using the long-term reward. Now, in this case, so far we have only discussed how to perform policy gradient with the Monte Carlo method. Now, full Monte Carlo simulation is best for episodic processes or processes which are relatively short. For very long-term processes, first of all, it gets computationally very expensive, because at each state you have to perform the Monte Carlo simulation to find out what the long-term value of that particular action was in order to perform the back propagation. Now, there is a technique called actor critic methods, which allow you to do this without using Monte Carlo simulation. So the idea here in Monte Carlo simulation is that you maintain two networks. You maintain a value network, which is a Q network with parameter W that estimates your long-term reward and advantage. So what you are doing with Monte Carlo simulations, now you are doing it with a value network. This is your critic. You call it the critic. The actor is your policy network, which we have already discussed. So you have two separate sets of parameters. You have a policy network with parameters theta that decides action. You have a value network or a Q network with parameter W that estimates the long-term reward or the advantage. So the advantage can be for example, your temporal difference. Or you can just use the Q value. It's up to you. But using the temporal difference has some benefits, as we discussed in the previous slide. And these two networks, in actor-critic network, they are trained simultaneously. So these parameters theta and W, you will learn them together in a loop. So both networks will get smarter simultaneously. So let's look at our actor network example. So here our actor network is the same as the policy network which we discussed previously, and this is the network which we'll be using to perform the simulation. So every time you have a state, you'll run it through a convolutional neural network. You'll get the probability of up, down, left, and right. That's going to change the state, but except that now the long-term reward as state, you won't perform the Monte Carlo simulation in order to find that out. You will input that state into your Q network to find out what the value of these actions were. So that is how you're going to use the critic network in order to calculate these long-term rewards instead of Monte Carlo simulation. That's the only difference. So the way in which the actor-critic method works is that you will sample the action AT plus 1 at state ST plus 1 using the policy network. So your policy network gives you probabilities of up, down, left, right, and you will sample one of that. And then what you will do, you will use the Q network to compute the temporal difference delta T at that state ST using the bootstrap target derived from the value of ST plus 1. Then what you'll do, you'll update the policy network using the Q value of action AT as its advantage. Now this Q value of action AT, you will get it from your Q network. Note that we are no longer performing Monte Carlo simulation. We are getting these Q values of the advantages of actions directly from your critic network, your Q network. And you can, instead of using the Q value, you can also use a temporal difference error if you want to do variance reduction. And we already discussed that in the previous slide. And then what you will do, you will update your Q network parameters. So you will update the Q network using the squared temporal difference as a loss. And then you will repeat these updates. By repeating these updates, the policy network and the Q network will be trained over time, simultaneously trained over time. Now, there are several advantages and disadvantages of policy gradients. In fact, policy gradients have been becoming more popular in recent years. One advantage of policy gradients is that they can work in continuous action spaces. So imagine you have a robot and your action for the robot is how many meters for the robot to move. So in this case, it's very hard for a value network to provide the values of all possible meters for the robot arm to move, unless you discretize the distance moved. In the case of a policy network, what you can do is that you can assume a specific probabilistic form to the number of meter moves. So you can assume, for example, there's a normal distribution with a certain mean and standard deviation, and the output of your policy network could be the mean and the standard deviation. So this is how you can model continuous action spaces. And then you can also use it for stochastic policies. So for example, if you have a game like rock, paper, scissors, then the outputs of a value network, they can be exploited, because the optimal policy in this case is completely stochastic, because you have to pick one of the three options completely random, and that can be shown to be the completely optimal policy. On the other end, a value network, which is deterministic, typically what it will output, that can be exploited by observing it. And another advantage of policy gradients is that they show stable convergence behavior. Now, there are also some disadvantages of policy gradients is that they can reach local optima. Policy gradients have become more popular in recent years because they have been shown to work very effectively in a wide variety of settings, and especially because of their stability. Now, in some recent work, even though I have not used bootstrapping, I have not shown how to use bootstrapping of policies, there is also some recent work, especially in the AlphaZero paper, which shows that policies can be bootstrapped by using Monte Carlo tree search. And details of that are given in the book.